Cast is now starting. All attendees are in listen-only mode.
Hello everyone and welcome to our AE member webinar for today, Tuesday, September 17th. Thank you for joining us this afternoon. Just before we get started, I'd like to go through just a few of our usual things. If you are joining us today, you will receive a follow-up email in the next 24 to 48 hours that will contain a certificate of attendance for today's event, but also a link to the recording for today. We are going to handle all Q&A at the end of the presentation. And if you would like a copy of today's presentation, please reach out directly to the presenter, who I will introduce to you in just a moment. Do feel free to post your questions throughout the webinar. We will just address them at the end. But as always, there are two sections on your control panel. There are questions and chat. In the question section, please post your questions for Mr. Eklund himself and anything that you have directly for me, perhaps technical question, anything like that, please post in the chat. Okay, so I am going to go ahead and introduce Mr. Eklund. Today we have Mr. Gord Eklund with us. He is Vice President of Marketing and Business Development for Triacta Power Solutions LP, and he has been a part of the management team there since 2009. Prior to being with Triacta, Gordon was a partner for a boutique venture capital firm, Venture Coaches, from 2006 to 2009, and also started a telematics company, Netistics Technologies, in 2002. Gord is a computer scientist and a technologist by education, and prior to Netistics, worked in technical management and sales roles in Mitel Corporation, Newbridge Corporation, and several small startups since graduating back in 1982. So thank you for being with us today, to both our members that are logged in and to Mr. Gord Eklund, and I'm going to pass over to you now, Mr. Eklund.
Thanks, Sharon. All right. Well, good afternoon, everybody. Welcome to this session on submetering best practices. I have a lot of waterfront to cover here. The presentation is probably a little over 40 minutes, so I'm going to go through it fairly quickly. Definitely, if you have any questions after and want to go over something that I've talked about, please feel free to reach out to me by email or phone, and we can talk about it. So it's not enough to measure. By that, we're saying that there's a significant bit of iceberg beneath what is showing above the surface of submetering. When planning a project that requires electrical metering or monitoring, property managers and building owners need to keep an eye on both today and tomorrow. How meters are deployed dramatically affects their usefulness now and down the road. Equipment selection, information strategies, financing plans, and regulatory requirements all play a crucial role in a properly planned and successful electrical submetering infrastructure. Emphasizing properly planned, this webinar will address types of electrical submetering equipment, industry standard information models and protocols for data mobility and vendor independence, information plan best practices for future-proof deployments, and ownership model pros and cons, for example, CapEx versus OpEx. The first question is, what is submetering? Well, we're all aware of that round glass-topped electrical meter on the outside of our buildings. This meter is owned by the electrical utility and meters all the electricity going into the building. The utility uses this meter to bill the property owner for their electricity. This is usually a single owner proposition unless the building was built with a view of the space being divided for multiple customers of the utility and metered directly as shown in this picture. That is typically not the case. Usually the utility meter remains a single meter, and that is where the participation of the utility company ends. Any metering within the building put in place by the building owner or manager is called submetering and is administered by an entity separate from the regulated utility. Now, just a little warning here, I'm going to use the term metering throughout this presentation, unfortunately, because I do that, but I really mean submetering. The next question is, why submeter? Submetering has become a foundational component of building management as electricity prices rise. There are a couple of reasons for this. Reason number one, to reduce consumption, it is essential to attribute the cost of consumption to the responsible party as accurately as possible. Historically, costs have been allocated by simply dividing overall building costs per tenant, but this is a disincentive for all tenants to take action. Reason number two, for the situation where one tenant or a single owner is responsible for a large and complex multi-stakeholder usage environment within the building, understanding where energy is consumed and where improvements are warranted is key to them reducing their consumption. Well, why are we looking to reduce consumption? Reducing consumption of electricity is a society-wide concern, as in most electrical grids, there's not enough capacity to meet peak demands with the least expensive generation capability, and often not enough capacity to meet the peak. Suppliers respond to this scarcity with increased time of use pricing, which can be very expensive. When 25% of commercial buildings' OPEX is utilities, it is well worth the focus. That figure comes from the Institute of Real Estate Management. It is even more compelling when studies have shown that management of consumption through application of submetering to attribute costs to the consumer is very effective. Perhaps the most exhaustive study of applying electrical submetering to commercial buildings was undertaken by the U.S. Department of Energy as part of the Federal Energy Management Program in 2007. This study showed that just installing meters resulted in up to 2% reduction through the Hawthorne Effect, which is the effect of people being aware that they're being monitored. That was just the start, though. FEMP found that the use of submetering as part of a coherent, continuous commissioning program of benchmarking, analysis, and remediation can result in from 15% to 45% savings. Quite a bit. So why continuous commissioning? Because psychological effects and operational prescriptions become less effective over time. Building usage also changes, causing a requirement for new methods and adjustments. In 2011, Canmet Energy, the Canadian leader in clean energy research and technology development, undertook a study as part of an ISO 5001 pilot program, using accurate submetering as the primary source of data. The use of continuous commissioning on one of their buildings at their complex in Bells Corners, Ontario, Canada, resulted in a 17% reduction of energy over 3 years. As you can imagine, this building was already a highly functioning building, given the nature of the organization performing the study. The costs avoided, $18,500 on a single building over the first 6 months of installing submetering. This resulted in an ROI of less than 1 year. In residential buildings with per suite submetering, Enercare Connections, Inc. commissioned Navigant to perform a study on the impact on electrical consumption of transitioning from a bulk meter, that utility meter, to submetering. Note, these suites were not electrically heated, so which is a much greater increase in electricity consumption. Navigant analyzed the data for 1,500 suites over 47 multi-unit residential buildings in Ontario, Canada. Based on paying for actual usage, the switch resulted in a 139 kilowatt hour per month average decrease per suite in the first year. This represented a 40% increase in average consumption. The economic case for using submeters as a tool to reduce consumption is compelling, with a payback in this multi-unit residential scenario of a little over a year, given the Navigant numbers. But that's not the whole story. The utilities and regulators responsible for supply have been active participants in the vast amount of research that has been undertaken over the past 20 years and are well aware of the effectiveness of submetering. Faced with increasing demand and the expense of adding generation, they see an alternative source of generation in megawatts, which is a reduction of consumption, and consequently are regulating submetering in commercial and residential buildings. In the US, based on this premise of the effectiveness of submetering, New York State, Maryland, and California have been leaders in mandating the application of submetering. It has also been addressed at the city level by many municipalities, such as Seattle and Austin. In New York, with Local Law 88 and Local Law 97, there have been clear directives on the mandatory application of submetering and energy reduction goals that necessitate benchmarking and actual reduction. In California, Title 24 sets criteria for reporting disaggregated electrical load types in a building. Granularity is the watchword. The more information that you have, the better the diagnosis that can be rendered on how energy is being used. Building codes as well are moving towards specifying monitoring right down to the branch circuit level. In short, submetering is proven to be economically effective in reducing consumption for the property manager, the tenant, and the regulator. Given that's good financially and becoming table stakes, you will be submetering. So what is available to you? Essentially, there are 4 choices to make. The first choice is determined by whether you have only a few single points of measurement distributed in different locations throughout your building. The best choice in this case is to use a single point submeter. This might apply if you only have a little bit of submetering that you want to deploy, or if the electrical plan of the building is such that you don't have big distribution panels, such as in the case of an older style multi-unit residential building with multiple electricity buses running through between the floors. The second choice you might make, if you have a collection of points in the same location that you would like to measure, but no need to deploy a lot of submetering, is to use a group of single point submeters in a cabinet. The advantage to using such a cabinet is simplicity. The downside is that it is not very space efficient. Third choice is for granularity and space efficiency. When you have many points that you want to measure and space is at a premium, a multi-point submeter will give you the smallest per meter point footprint and the lowest per meter point cost. The fourth choice, the fourth decision point, relevant for all of the previous 3 configurations I've just mentioned, is whether you want to go with a metering solution, which might allow you to bill, or whether you're just looking to use the instrument as an energy monitor. Electricity distribution in buildings, even multi-tenant buildings, is evolving to centrally located panels in electrical rooms and closets, a trend driven by safety considerations as it allows a service to be shut off in a very precise, localized fashion, as well as convenience and practicality. This presents an opportunity to aggregate meters in one physical space, and in fact, in one piece of equipment, the multipoint submeter. Multipoint meters create an opportunity to be more granular in measuring based on lower meter point cost, and therefore allow greater precision in analysis of electrical usage. Single point electrical meters can still be used for in-suite applications or point purposes where low meter point densities are called for. For example, the +1 meter or a retrofit scenario where multipoints can't work. Electrical meters or monitors are either jaw-based, typically bulk meters, or CT-based, that's a submeter. As we mentioned right at the start, a bulk meter is the glass-topped meter used by the utility, and there's usually one per building, except in the case of some multi-unit residential buildings, more specifically probably condominiums, where units are directly billed by the utility. When this meter is removed, it actually shuts off the flow of electricity. Submeters, an example shown on the right, are typically CT-based. CT-based submeters use current transformers or current transducers to measure the current through a conductor when the conductor is passed through the CT. The current, when coupled with the voltage reference acquired from a point in the panel, can be used to calculate power. The CTs are connected to the meter by leads that are typically attached to the CT, although there may be longer cables spliced to them. Meters versus monitors. Well, when used for billing purposes or the basis of a monetary transaction of some kind, the measurement instrument must employ certain features that are controlled by a regulator, such as accuracy, physical security, and displays. If the device is not being used for a financial transaction, that is just to monitor consumption for management purposes, some of these features can be skipped and the device is called a monitor. This cost difference between a meter and monitor is becoming negligible, especially in the case of multipoint meters, which can defray the increased feature cost over multiple points. So it's becoming impractical to use a monitor when it's compared to the advantages of having certified meters in a place that can be used to bill or need indisputable traceability. So what are the extra features of regulated submeter versus an unregulated monitor? A submeter must have a local display, even if it is being read remotely. What is shown on the display, how it is navigated, and how it appears is usually dictated by the regulatory body that has local jurisdiction. Some jurisdictions are okay with plus or minus 1% accuracy, but plus or minus 0.5% is the more common accuracy going forward, and is determined against a performance specification set out in American National Standards Institute ANSI code C12.20. Since submeters are usually in a relatively sheltered environment, the typical specification for their environmental enclosure is a standard called NEMA 250. The integrity of a meter is key for ensuring that a financial transaction is valid. Physical mechanisms must be provided to ensure that the unit's ability to correctly measure is not tampered with unless evident in some way. This is usually achieved through the enclosure of the device and the use of seals. In this case, the seal is a little red thing at the bottom, circled with a yellow circle, that must be broken to open the device. In many jurisdictions, this seal is applied by the meter provider at installation. In some jurisdictions, there's an extra step where the meter is verified to be within specified limits by an accredited shop, and a seal from this meter shop is applied. These two pictures show a sealing mechanism with a programming switch underneath that must be reached through the seal to prevent programmatic changes. The seal is applied at the slot in the metal bars. These criteria are dictated by the local jurisdiction under building code and law. Often the source reference specification for such criteria is ANSI C12.20, although some jurisdictions go beyond that. The jurisdiction may do all the compliance testing themselves, or they may rely on the testing done by jurisdictions that have already done it, or on accredited third-party labs, as this often requires special equipment. As examples, in Canada and California, primary testing is done by the Weights and Measures Authority. In New York and Maryland, some physical inspection is performed, but there's considerable reliance on third-party lab testing for the actual measurement performance. A final note on meter versus monitor. Regulatory bodies take a great deal of care in their specifications to promote reliability, as these devices are expected to be left in the bowels of building infrastructure for 20 years or more, all the time operating reliably. This supercharges the payback on these devices versus something that might cost a little less upfront, because one of the most costly elements of ownership in a metering infrastructure is the dreaded truck roll. Current transformers are solid core ring devices which the conductor passes through. The device on the right is a solid core current transformer. The service must be disconnected to be passed through them. Split core transformers, like the device on the left, and Rogowski coils or rope coils, shown in the middle, are current transducers, typically reflecting changes in current by changes in voltage on the device's secondary. They are easier to install as they come apart, allowing the CT to be applied without disconnecting the electrical wiring from the panel breaker. But be careful, although this looks like an end run around the difficulty of installing a solid core. Most electrical codes and common sense tells you that the work should be done by a licensed electrician and the panel should be shut down, even if you are not disconnecting the service. These devices are rated with a primary current and a secondary current. For example, 200 amps to 5 amps, or 200 amps to 100 milliamps. The way this works is that when the current in the conductor is at the maximum, the current on the secondary is at the maximum rating, and the secondary current varies proportionally with the current on the primary. For instance, with a 200 amp to 5 amp CT, 200 amps delivered to the load would develop a 5 amp current flow on the secondary. A 5 amp meter would detect the current and use the voltage reference to calculate power at any instant using Watt's law. Early meters and CTs were typically based around the 5 amp secondary. This is still useful for very large primary currents that are typical of building level load and high voltage equipment, but it's a dangerous current, and the transformers are larger and more expensive. Modern meters, or more recent meters, are based around the milliamp standard, which is typically 100 milliamps on the secondary. These CTs are smaller and less expensive, and the current level won't kill you, which is a bonus. And they can be placed much farther away from the load being measured, as much as 100 meters or 300 feet. This is because the low current doesn't develop a significant potential through the CT lead. So elaborating a little more on split core versus solid core. As primary load specs go up, for instance, to measure a larger load, the CT gets bigger, and typically the aperture through which the conductor is fed becomes larger. Of course, this increases cost. Current transformers, solid core versus split core current transducers or split core current transformers, need to be used if the meter is to conform to the ANSI 12.20 class 0.5 specification for accuracy, as a split core typically can't meet the accuracy requirement the specification dictates over the range of conditions required. Solid core current transformers are more difficult to deploy, especially in retrofit conditions where panels are already built and in service. It may be convenient to use a split core current transducer, which converts the primary current to a proportional output voltage, which is most often 333 millivolts, if you are only in a monitoring situation. Split core transformers are typically bigger and more expensive than equivalently rated solid core current transformers, but have the advantage of this hinge so they can be installed without disconnecting the service. And the accuracy is typically less than plus or minus 1%. That means worse than plus or minus 1%. A similar current transducer is a Rogowski coil or a rope coil. These are very useful when the aperture of the device needs some flexibility. That is, you're probably not sure what you need, so you just buy this as it's almost one size fits all, and when the currents are quite high. The output of these devices is a very low voltage, which must be amplified by externally applied active circuitry, which will require some kind of external power, unless the meter you've selected has a built-in amplifier. These devices are more expensive. Now, either split cores or Rogowski coils are appropriate for financial transactions. In this whole process of metering, of course, the first step is a metering design, assuming that this is not just some clear-cut single-point metering requirement. Two key questions to ask. What are you trying to meter? A few easy answers to this are, where possible, any electrical system down to an indivisible piece of equipment, individual tenant premises, or any electrical services such as heating, HVAC, lighting, plug loads down to the tenant level. The second question to ask is, how can you match the metering system to the electrical infrastructure of the building? This is largely about panels, current loads, voltage references, and the configuration of the meter that you're using. The single line drawing is the key source material which will yield a meter design. Of course, this is easily available in a new build, but notoriously hard to obtain on an existing building. In the case of an existing building, a site walk involving facilities management and an experienced consultant is essential. It may add some additional costs, but will pay off in avoiding the inevitable incremental costs that will occur when unforeseen difficulties arise. In the case of multi-unit residential buildings, the bulk of the metering intent is somewhat regular and straightforward. You are metering suites. Even then, however, there are common facilities that must be managed and therefore metered accordingly, requiring some expert assessment. The ease and method of installation is affected dramatically in any metering situation, depending on whether it's a new building under construction or if it's a retrofit situation. In a new build, most things are relatively easy. In a retrofit scenario, the complexity increases in leaps and bounds. With new buildings, the metering design should be considered from the start. Accommodation for physical placement and communication are wide open and can be achieved if the builder desires. Access and space are key requirements that must be paid attention to. Communications is better if it's wired, and this can be easily accomplished in a new build. Other alternatives are powerline communications and wireless communications. But if you're building the metering with the rest of the structure, you can't beat wired for reliability. Physical space for a multi-point meter must be planned for, but in a new build is relatively easily accomplished. In these shots, we show a commercial installation on the left and a very dense residential installation on the right. The latter had a very small closet space and metering added after the closet was designed. So some fairly innovative three-dimensional bracketing had to be thought up, if you notice in the picture. To reiterate, space is one of the easiest wins when using the true multi-point CT-based submetering versus multi-point single-point meters or job-based meters. In this picture, which you've already seen, you have quite a few single-point utility meters being shadowed by a single revenue grade multi-point meter, which is circled in the with the yellow circle. As you can see, it's a lot more compact than that meter center. In fact, there is an opportunity to even place the multi-point meter in the panel tub, although this has trade-offs when ensuring that regulatory issues can be met. For example, meters that need regulatory approval are usually subject to periodic inspection and re-verification for accuracy, which becomes more difficult with in-panel metering. If you're going to go that route, ensure that you understand the requirements of your jurisdiction. This is where you might get some kind of a split between the people building the building who want to go this route because it's easier than the people who actually ultimately own and manage the building. Whether a new building or a retrofit, but especially when there are many meters being deployed, it is important that there's a clear record of what circuit is related to which meter and in what way. Here's an example of such a record. It is useful, in fact, in my opinion, critical to create an installation record for each meter that can be used by electrical contractors to ensure each CT is connected in the right way to the meter, that is, the right meter point. Even better is for this record to be automatically created by the metering management system that you'll be using. Yes, these things exist, and stored there to be reviewed whenever there's a question about the metering system or any changes to be made. The mechanisms for connecting the CTs to the meter proper are important, not only for initial error-free installation, but also because there will always be a point where the two must be separated, whether that is from a failure or because the meter must be removed for verification. When CTs have been installed and power is on, if the CT is disengaged from the meter, there must be a shorting mechanism to ensure that a lethal current does not develop across the open leads and kill the guy who's taken out the meter. This is a mandatory requirement for 5 amp CT secondaries, which has been continued for milliamp CTs as a safety precaution. Historically, meters have provided screw-down termination blocks to land the CT leads from inside a panel on a shorting frame. Although this is simple to understand and electricians are used to it, it is more time-consuming and error-prone. Leads must be fed from inside the panel to the termination frame, which is outside the panel, when the meter is not installed in the panel. The right position and polarity must be observed. Electricians have methodologies for keeping this straight, but it's all time-consuming and usually means labeling the leads manually. When you're paying a ticketed electrician to install, you really don't want the process to drag out. More modern methods consist of structured cabling with color-twisted pairs that can either terminate on screw-down connectors in the meter enclosure or are grouped into multi-pin connectors. These cabling methods may integrate shorting, so there's one less thing to consider. They also facilitate a separation between the panel CT installation and any work that involves the meter system itself by just unplugging the cable from the meter. Meter installation requires certified tradespeople to install, and in the case of electrical meters, that means electricians. Because of the expense of a licensed electrician, it's preferable if the involvement of the electrician can be limited to the direct connection of the CTs to a termination solution for the meter, and all other stages in installation be left to other craftsmen or technicians. That is, communications, deployment, commissioning, re-verification. Commissioning is the process of ensuring that the meter is measuring the correct loads. This is a trivial task in a new build, but in a retrofit, it's a multi-person task that involves going through the entire building and ensuring that the meter is properly measuring the expected load. This work will to some extent be replicated when an inspection is performed by a regulator via a properly authorized agent. In some jurisdictions, such an inspection can happen up to a year after initial commissioning and the system is put to use. That's not the time to figure out that your metering wires are crossed. Finally, in an approved metering scenario where financial transactions are occurring, there's often a process of re-verification of the meter by an authorized agent. This may be done in a statistical sampling of a population of meters from the same manufacturer built at the same time, but can also be simply re-verification of every meter point in the building. This can be performed in situ with special equipment or on location with special equipment, but more simply performed by removing the meter with the CTs in place and shorted, and temporarily or permanently substituting another meter. This demonstrates both the need for an elegant mechanism for inserting and removing the meter from the CT termination and for managing a meter changeout at the reporting level. For want of another example, I'll show how the Triacta gateway accomplishes this. Here we have a meter base where the CTs have been landed on those structured cables I mentioned down at the bottom of it. Now we take a multi-point meter, in this case capable of metering 16 three-phase circuits. It's inserted into the fixed cabling, which is shorted when the meter is not present. Now the utility cover is put back on, and your meter is back together. And of course, taking the meter out would have been the exact opposite process. Submetering is a strange little niche in the building ecosystem. with very modest roots as a passive walk up and read system. It is often seen as something standalone and separate, and often too little forethought goes into how the information in the meters should be handled. This is a terrible mistake. We have made the case with this presentation that the submetering system has fundamental information on how a building is performing, information that can be leveraged to save considerable amounts of money. Given this, at a minimum, at least half the thinking and effort put into a submetering project should be put into capturing, communicating, and using this information. The components of the information plan are communication infrastructure. Believe it or not, the vast majority of submetering projects still anticipate physically walking up to meters and reading them from their displays. Many systems use simple serial communication buses such as Modbus to present metering information to a collector device or building automation system. That is fine if one exists already, but if not, it potentially adds another point of failure. What is more compelling today is the use of cloud-based applications. This implies a direct path to the internet by Ethernet or a wireless link. Since needs change over time, it's smart to choose a solution that allows multiple communications paths. Information persistence is how the metering information is preserved. At one level, this looks straightforward. Once it is off the meter, it is preserved in the management system. However, it's important to consider the scenario where the meter is cut off from the collector or the internet for a period of time for one reason or another. In this situation, it's important to ensure that data can be preserved in a stable fashion with as little loss as possible. Some meters, particularly those designed to work with cloud applications, provide mechanisms to store metering information for periods of communication loss, indeed up to 2.5 years perhaps. Once communications are restored, they report all the saved information. This makes recovery from unforeseen circumstances easier. Since the metering information can be used for many purposes, the submeter should be able to be read by simple collectors, building information systems that perhaps use common protocols such as MBus, Modbus, but probably most importantly, BACnet. But the model of the future is push information to applications in the cloud. The great thing about the application as a service model today is that information from meters can be used for many purposes, from billing to energy management, to compliance reporting, to demand response, to diagnostics. In fact, the big data model of the world can yield information about building usage and performance that you don't know you need or even have today. I should say. Information should be captured, communicated, and preserved in such a manner that it can be easily retrieved in either a processed or raw format to be passed on to new applications as they come online. And there are a lot of them. It really isn't the topic of this discussion, but it should be noted that there are many applications in the cloud that can be used to derive value from your metering data. Some of the more forward-looking uses of meter data, demand response programs, which may be leveraged or even imposed by local jurisdictions. These require awareness of many external factors, including the global adjustment rate, shed load calls, or the utility price signal. Distributed energy resource opportunities, local microgrids, and blockchain transactions. This implies not only mobility of data in the cloud, but locally in the building to local intelligence. This can be handled by multiple communications interfaces, supporting a push and pull model, and even multi-homing push of files. Extraordinary tenant load correlation, such as electric vehicle charging. That is, correlating your electrical vehicle charging from the parkade with your suite bill. This implies being able to label information or tag it to be able to correlate between different systems. Common equipment fault analysis, such as rooftop unit operations, by tagging the information and analyzing normal operations versus anomalous operations, while considering extraordinary circumstances such as external weather conditions. Suffice it to say that the future proofing of your information plan, supported by your system choices, should not be neglected. The historical models of information planning are not the way to go. Short-sighted behavior today will result in considerable restrictions for you down the road when your needs change. Security. Note that with this evolution in terms of communication and networking and direct connection of devices to the internet, there's an impending security gauntlet that is going to need to be traversed. With the rise of botnets formed from primitive IoT devices such as networked cameras, jurisdictions are writing laws that will ensure these devices are appropriately secured. One of the pioneering laws in this space is California's Connected Devices Law, Title 1.81.26, which goes into effect January 1st, 2020. This law will definitely evolve, and copycat laws are already being formed in other jurisdictions. Therefore, technology that can adapt should be considered when making buying decisions. Ownership models. Well, we've gone all through the technology aspect of things. Now we're going to talk about perhaps how you should manage the whole process. So even though the studies have clearly shown the submetering is well worth the expense and effort with a quick and high return, you can see that submetering to the granular level has complexity and expense involved, including meter system design, project management, installation, commissioning, regulatory compliance where applicable, and systems and reports training. You may now have gotten cold feet and decided to defer going forward with submetering. But you can see that it's not only a great ROI, but probably something that's going to be mandated in the future. So how can you accomplish it besides just doing it yourself? There are 3 common deployment ownership models that, depending on your company's business goals, technical capabilities, and economic strategies, you will want to consider. The do-it-yourself model, where you buy, install, and maintain the equipment and billing energy management processes, has the potential for saving money on ongoing service fees and installation costs. But given the complexity of many submetering initiatives, may end up costing much more in the long term due to unforeseen deployment issues and commissioning complexities. This model carries both CapEx and OpEx expenses, with high upfront equipment purchasing costs and ongoing operational expense of running the system and deploying billing and energy management programs. Buy and outsource. This model simplifies deployment and operations by having outside metering professionals handle system setup and potentially ongoing operations. It carries the same high upfront capital costs, but leans on outside expertise for setup and operation. Turnkey. This approach is growing in popularity, where metering equipment is leased and all installation, maintenance, and ongoing management of energy management or billing program management is outsourced. This is a complete OpEx play where upfront costs and project deployment and operation risks are avoided by entering into a service fee-based contract. And finally, at the end of the day, this turnkey solution might be the way to go, especially if you can avoid a big immediate CapEx decision. But it is still important to ensure that your service partner will fulfill all your requirements. Hopefully, we've made you a little more prepared for all the aspects of the metering project when you want to engage. But one caution about this: it's great until the day that you decide you want more information, which their system cannot develop, or a different presentation format, which is subject to incremental consulting project fees, or ultimately you want a new vendor and discover that all your historical data is owned by that vendor, by the old vendor, in either unavailable period or at further cost. The antidote to this situation is very clear instruction and agreement at contract time as to what the partner is going to do and what your rights are with respect to data. Great vendors compete on the basis of a better product, not customer ignorance. Know up front that complete ownership of your data is vital and at stake if you don't take care. And that is it for me. Thank you very much, and open to questions. I see I went pretty long. I'm sorry about that.
Thank you, Gord. We do have a small number of questions. I don't know, can you see them there? The first one that came in was, any experience with regulatory findings that submetering makes the building owner a utility?
I don't have any experience with that. The jurisdictions that we typically operate under are very clear about what submetering is. And, you know, where there's going to be any distinction or any confusion where submetering is allowed, it's fairly clear that the submetering company is not allowed to charge for the electricity itself, but they charge for the fee, they charge for the privilege by just adding a management fee onto the cost of generating the bills.
Okay, thank you. Says, I like the box with CT installed. Any suggested brand?
You like, well, that particular box was a Siemens box, was a Siemens panel. There are several places where, and you know what, usually what happens is you have a panel manufacturer and they design the panel around a particular a meter that you may choose. And most meters are able to be put into panels. So that particular one was a Siemens. Siemens box. You can get a similar box from Eaton. You can buy the Triactive meter. So you know, I think that you're in the near future, you're going to see meters that are tailored to being put in a panel, as that one was.
Okay, there are a couple more, but just before I say that, just a reminder, everybody, if you do want copies of today's presentation, you do need to email Gord directly. I'm saying that now while his contact information is on the screen for you. So if you do need to do that, please go ahead and make a note of Mr. Eklund's contact information. Okay, next question. Any IoT submeter?
Well, you could consider a meter with an internet connection, whether it's Wi-Fi or Ethernet, or connected via a cell modem to be an IoT meter. I'm not sure that I know of any, and I'm talking about submeter. There are lots of small single-point energy monitors or meters that do have wireless links in them. I'm not sure that you have any with a real proper LoRa or you know, name your IoT brand of wireless connection to them. But anything that's actually connected up to Ethernet and is using internet protocols is actually an IoT device.
Okay, thank you. What data collection interval is most common when submetering?
It depends on what you want to do. If you just want to bill a tenant for straight kilowatt hours, then a 60-minute interval is fine. If you want to start looking at demand and time of use, then you want to start using, say, a 15-minute interval. Again, that is fine when you're talking about the generic regulator tariffs that are out there. If you want to get really tight, you can go down as low as 1 minute intervals. But
thank you.
But the specifications really are around 15 minutes for demand.
Okay, let's see. We've got fantastic presentation. And then next question. In electrically heated buildings, submetering could potentially cause occupants to be billed unfairly for heating loads. For example, heating units on the top floor using much less heat than the bottom floor. Are there any regulations that protect tenants against this?
Yeah, I can't speak for all. Cannot speak for all jurisdictions, but for instance, in Ontario, you are not allowed to submeter billing. Submeter or bill for heating. You can submeter it and see how much is being used, but you can't bill for heating. That's a little different when it's say a condominium setting and the meter's actually probably being used for the whole utility, and the occupant owns the premises. But like I said, in a rental situation in Ontario, it's not legal to bill for heating. I can't speak for New York or Maryland or California, which are the primary jurisdictions in the U.S. that allow submetering.
Okay, next question. Is Siemens BACnet compatible?
Oh, that's a good question. I'm not sure that particular meter is BACnet. I wouldn't bet against it. But if you send me an email, I can refer you to that model. That particular model is approved for NYPSC. I think it's Modbus, but send me an email and I'll send you the model number, and I'll get you the information to show it and send it to you.
Okay, then does the Triactor web surface support the utility and industry standard REST API?
Well, REST API isn't an industry standard, and our meter does not yet have a REST API. We are going there, but right now we use FTPS and push flat files up to the cloud. Or you can query our meter as a BACnet slave or a Modbus slave from a building automation system.
Okay. Quick question for me. Will a recording of this webinar be made available? Yes, as always, you guys will receive a follow-up email containing a link to your certificate of attendance and a link to the recording of today's webinar. Then question for you, Gord. Any comments related to wireless submetering?
So one thing you do have to watch out with wireless submetering, say if you're using Wi-Fi, sometimes when you're doing submetering on a building, you don't have the density of devices. In other words, you have a distance between your units that won't allow you to use Wi-Fi dependably. If you have more of a mesh network with a lot of transceivers, then that's completely fine. You know, certainly wireless is good when you're in a retrofit situation, because definitely communications in some of these older buildings is difficult, and installing the communications is just easier when you're using wireless. But if it's a new building, I would go with wired, because that's just the most dependable.
Okay. Are there any utilities offering financial incentives to implement submetering?
Well, I would say that in New York, there are programs which will, and I think most utilities and most jurisdictions offer incentives install submetering, which amounts to paying a certain amount for to help you out with the cost of the equipment. I can't give you any specific examples because these programs change all the time.
Okay, we will make this the last question and then we will wrap up. So it says, did you recommend, we've got more dropping in right now. Did you recommend the industry use power monitoring expert Schneider software, or did you recommend another one?
Oh, I'm not going to recommend any. I think there are a lot of good options. There are a lot of different, and I won't say anything bad about Schneider for sure. But there are a lot of different software applications out there and systems that you can use that are quite good. So I'm not going to recommend it, but I'm not going to not recommend it. I remain neutral.
Okay, next question is, we've got two. I'm going to take these last two. So if you have any further questions, please hold them at this time and you can email them to Gord, but I will take these last two that have just popped up. Says, this webinar was focused on electrical submetering. What appetite is seen for gas, water, CHW or steam submetering in customer verticals or geography?
Well, water is after, not, and I'm not going to say after electricity, water is definitely the most popular form of submetering in the United States. And it is rapidly becoming very popular in Canada. Gas and thermal are less popular, but eventually I imagine that they will also become very important. But water is tremendously important in the U.S. I did not discuss those utilities in this discussion because I'm more familiar with the electrical situation.
Okay, and then does triactometer communicate with BACnet MSTP gateway via RS485 cabling?
Do we have to? We don't. In fact, we don't have an MSTP interface. We use BACnet Ethernet, BACnet TCP/IP, or BACnet IP, I should say. In Modbus TCP/IP, we do have a Modbus RTU over RS485 interface for our older PowerHawk meters, and we use FTPS to communicate over Ethernet to servers. And as I said, watch this space for the REST interface.
All right. Well. Sorry, everybody, I was muted. I apologize. Follow-up email will come out in the next 24 to 48 hours. That will contain the link to the recording of today's webinar, plus your certificate of attendance for today's webinar. So we would like to say a huge thank you to Mr. Eklund today for being here and sharing his expertise. And a huge thank you to all of you who've tuned in today. Just a couple of quick reminders. We are going to be in Washington, D.C. next week for our AEE World Energy Conference and Expo. We hope to see many, many of you there. I look forward to meeting many of you. And our next AEE member webinar will take place on Wednesday, the 9th of October. It will be presented by Kimia Yegane, and it will be Lessons Learned in Measurement and Verification. So please join us on that one. Thank you everyone once, and have a wonderful afternoon. Goodbye for now.